Well, welcome to 2.5, the Fundamental Theorem of Algebra. If ever there is a lofty title to a section, the Fundamental Theorem of Algebra would be it. So here it is. It says if we have a function that is a polynomial, like 3x squared minus 2x plus 4, there's x terms, they could be raised to integer powers, then there's at least one zero if we're in the complex number system. So we can have i's involved in there. Because of course, here's y equals x squared plus 1 looks like this, and it does not have a real zero. But it does have apparently at least one zero in the complex number system. So that's it. That's the fundamental theorem of algebra. And why this doesn't get that grandiose name is beyond me. Because take a look at this one. If f of x is a polynomial of degree n where n is greater than or equal to 0, then f has precisely n linear factors. That means it has precisely n zeros in the complex number system. So if n is 5, this says, well, there's at least one 0. If n is 5, this tells us there are exactly 5 zeros in the complex number system. So this completely trumps that one. Okay, complex zeros occur in conjugate pairs. Now, we did some problems in the last section where we got some complex zeros from some polynomials, and that occurred when we went to the quadratic formula. Opposite of b plus or minus square root of b squared minus 4ac all over 2a is our quadratic formula. And if you look at that, where are we going to get imaginary numbers other than in square roots? If this square root becomes negative, if this is a negative inside of the square root, then we get imaginary numbers, and look what's out in front of it. And what is a conjugate? A conjugate is like 3x minus 4. The conjugate is 3x plus 4. There's our plus or minus right there. This is a really useful formula for us. And if you read this, it's almost like this doesn't need to be there. Sometimes mathematicians in explaining things cloud them up a little bit. Complex zeros occur in conjugate pairs. That's it. Like linear factorization theorem, well, I need some explanation. I don't need an explanation from this. If 2 plus 4i is a 0, then 2 minus 4i must be a 0 because complex zeros occur in conjugate pairs. Don't really need that if I understand complex zeros occur in conjugate pairs. So there you have it. Okay, factors of a polynomial. Every polynomial of degree n is greater than 0, so it's really just like the first two fundamental theorem of algebra and linear factorization theorem, with real coefficients can be written as the product of linear and quadratic factors with real coefficients where the quadratic factors have no zeros. And you'll see how that just falls into place with what we just talked about in the linear factorization theorem. So with no further ado, let's get to it. Quick reminder, I like to throw this out there every now and then. You are expected to have the notes that I have on that prior page as part of your homework assignment. So here we go. Now this is a matching, and I didn't feel the need to put what they're going to match with. So we're going to kind of treat this where it says match the function with the exact number of zeros. And understand, we're working in a section that's dealing with complex numbers. So they're just saying how many zeros would this polynomial have? It has exactly n linear factors, and every one of those linear factors would be a 0. So 5 zeros. We may not know what they are at this time, but that's not what it's asking. X minus 14 is x to the first 1, 0. Okay, that's just emphasizing we understand the linear factorization theorem. Now, confirm that the function has the indicated zeros is as easy as this. It says 0 is a 0. Let's see. F of 0 would be 0 cubed plus 9 times 0, which is clearly 0. F of negative 3i would be negative 3i, all of it cubed, plus 9 times negative 3i. Let's see, that is, the negative survives here. I get negative 27 I to the third plus negative, positive times negative, minus 27I, but I to the third is I squared times I. This is just my little thought bubble right here. I to the third is I squared times I, and I squared is negative 1. So this is negative 1 times I, negative 27 times negative 1, positive 27 times I minus 27I is 0, and we've got it. And you're going to see this next one very, very similar. Put in 3I. By the way, complex zeros occur in conjugate pairs. What's the conjugate of negative 3i? 0 minus 3i. The conjugate of that is positive 3i. So f of 3i, and I could go through this algebraic argument, but since negative 3i is a 0, and 3i must be a 0, because complex zeros occur in conjugate pairs. You want to go through the algebraic argument, that's what the book's expecting you to do, but this is the way mathematicians like to work. Hey, listen, I've already shown, or we've already been told that complex zeros occur in conjugate pairs. If negative 3i is a 0, 3i must be. And we showed that negative 3i is a 0. So there you go. Likewise, once I show that negative I is a 0, I don't have to show that I is a 0. They're conjugate pairs, 0 minus I, 0 plus I. So f of 0 is 2 times 0 to the 5th minus 2 times 0, which equals 0. Check. F of 1 is 2 times 1 to the 5th minus 2 times 1, which is 2 times 1 minus 2 times 1, is 0. Check. F of negative 1 is 2 times negative 1 to the 5th minus 2 times negative 1, which is 2 times negative 1 to the 5th is negative 1, which is negative 2, plus 2, which is 0. Check. And f of, I'm going to go with f of I here. F of I is 2 times I to the 5th minus 2 times I. Well, I to the 5th is I to the 4th that we talked about. We talked about that in the last section, but I to the 4th is I squared times I squared. That's negative 1 times negative 1, 1. I to the 4th is 1 times another I is just 1 times I minus 2i equals 0. Might want to rewind that, listen to that. And then if I call this guy right here, this explanation right here is star. F of negative I is 0 by star. Same reason. Just a little abbreviation there. You are welcome to use that, but you can't just assume going forward that when you take a test you can start with star. I had to establish star little quote to use that. Okay. Then find all the zeros of the function, and they've graphed this for us. And that makes me think that -2 appears to be a 0. Can I be certain? No. If there was maybe a dot on there, maybe. 2 appears to be a 0. 4 appears to be a 0. And what I could do is I could start synthetically dividing from 2 sections ago. -2, see if I get 0. 2, see if I get 0. 4, see if I get 0. Or I could try, say this, f of -2, let's see, that's -2 cubed minus 4 times -2 squared minus 4 times -2 plus 16, or let's go -8. Let's see, +4 times -4 minus 16, -8, 4 minus 16 minus, this becomes +8 plus 16, it equals 0. And we could do it that way. We could also, and of course we'd need to check, does 2 work, does 4 work? We could also say, hey, does this thing factor? If it does, it factors by grouping. So this is a possibility for you, and I'm fine with you continuing that process. But I could also try to factor this thing. Does it set it equal to 0 and factor? Does it factor by grouping? Here's a big hint. Check this ratio. 1 is to -4 as -4 is to 16. And that is true. 1 on -4 is the same as -4 on 16. This will factor by grouping. I don't know if you've ever been told that before. Check that ratio. 1 is to -4 as -4 is to 16, or 1 on -4 equals -4 on 16. So I'm going to factor by grouping. I'm going to get x squared out of the first 2 terms times x minus 4. And then I need to get another x minus 4. I need these to match. Can I do that? I can if I factor out a -4. And now I can factor the -4 out of both terms. Oops, just x minus 4, sorry. I get x minus 4, factor it out, and I'm left with this x squared minus 4. So x minus 4 times factor this difference of perfect squares. X equals 4 and plus or minus 2, and those are our zeros. Now, for your number 13, we say, well, it looks like 4 is a 0. Well, yeah, guess what? 4 is a 0, but there's 2 more zeros that are solutions to this by the linearization factor rule. There's 2 more imaginary zeros. You'll see how we handle that, because this must have 4 zeros. Okay, so there we have it, and it says, and all 3 of these are real numbers for number 14. You're going to have 2 complex numbers and 1 real number, 0. Is there a relationship between the number of real zeros, 3, and the number of x-intercepts, 1, 2, 3? Yes. And explain, well, real zeros would be, or maybe better to say are, would be x-intercepts of the function. I mean, it's pretty clear. If f of x is my y, any value of x that turns that into 0 is going to be plotted on the x-intercept. Let's see. I might reuse that. Let's call that one triangle. Okay. So options. I could say, hey, I think 2 is a 0, synthetically divide it through this, expand that, and synthetically divide it, and then divide the result by -2, and you're down to a quadratic. And then we're going to go to quadratic formula, because that's where those 2 imaginary zeros or complex zeros are going to come from. But we could also try to factor. x to the fourth, x squared, no x's. This is quadratic on x squared. It might factor into x squared, x squared. Factors of -4 that add up to -3, -4, and +1. Oh, okay. So this is x plus 2, -2 is a 0, times x minus 2, +2 is a 0. And check this out. I bet anything, maybe most students at some point have tried to factor this thing into x plus 1 times x plus 1. And by now we should realize that doesn't work, because if I FOIL x plus 1 versus with x plus 1, I get that middle term. I don't just, when I take x plus 1 times x plus 1, I don't just get x squared and 1. Got to go through the FOIL process. However, watch this. X plus 1, or x plus I, x minus I, that would give me x squared, good, minus xi plus xi cancels, and then watch this. Negative I squared is the opposite of I squared, but I squared is -1, the opposite of -1, +1. Listen closely and let this one sink in. The sum of perfect squares is factorable, just like the difference of perfect squares, but we need i's involved. So the sum of perfect squares, if we're dealing in complex numbers system, is factorable. So our zeros are x equals plus or minus 2 and x equals plus or minus I. And yes, there's two real zeros. There's two zeros, or there's two x-intercepts by triangle. All right, which you are welcome to use, but again, you have to establish triangle. I've got a triangle established. You can use it over here. There's a reference for it. It's like a key. Okay, so 17-minute video, a lot of explanations along the way, probably 12 minutes or so assignment. As always, let me know if I can help.